something a little different on the bench this time. It's a Casio DH-100 digital horn. And this is a wind controller that was released by Casio in 1988. And for a wind controller of that period, it's got a pretty good set of features. There are 6 built-in sounds. There's a saxophone, trumpet, synth reed, oboe, clarinet, and flute. And they're listed here on the back because there's no screen. You just cycle through them. There's a volume control here on the side and a built-in speaker in the bell of the horn. This has quite a lot of weight. The magnet in the speaker is quite hefty. It uses basically a standard recorder style fingering. There's a few extra keys. There is a thumb key, and there's one extra key here at the top to turn portamento on and off. On the left-hand side, there's a button, and that cycles through the tones that are listed on the back here. And there's a transpose button, and as you press that, it will cycle through half semitone steps up and down an octave to transpose the whole horn. There's also a breath on and off switch. When the breath switch is in off, just pushing the keys down is enough to make the horn make a sound. When the breath switch is on, you actually have to blow through the mouthpiece. There's a wind sensor. There's no pitch sensor, so there's no lip control, but it can detect the intensity of the pressure of the breath that you're blowing into the horn. On the other side, there is 1/8 inch style headphone output that's also a line output. Power on off. There's a power jack for DC power. It's a little weird. It's 7.5 volts, sensor negative. And there's also MIDI out. So in addition to the key that you're playing, the note that you're playing, the note on and off, the wind sensor will also output aftertouch data. And we'll look at the MIDI implementation a little later. There's also a battery compartment here on the back, and it takes 5 AA batteries if you want to go completely mobile. And there's also a thumb rest for your thumb, which is pretty standard for this type of wind instrument body. And there's also a chin strap hook if you find this too heavy to hold. The problem with this particular unit is that the power is very flaky. It kind of turns on and off. I can't get it to work at all with batteries. I tried batteries. Here I've got a generic wall wart adapter. Let me plug it in. And I am checking. It's at 7.5 volts, center negative. So there's nothing wrong with the power. And it's the smaller 2.1 millimeter internal pin. So I'll plug it in. And so if I turn the power on with the adapter plugged in, nothing happens. The LED doesn't light up. But if I kind of, sorry about flipping this around all over the place. If I kind of wiggle it a bit, oh, there we go. Oh, something's clicking. So you can see, oh, and then it turned off. So you can see the power LED kind of turning on if you hit the sweet spot. And I can hear the internal amp turning on because I'll suddenly get a click from the speaker. I suspect that there's some mechanical issue. So the next step is simply to take it apart and see what the issue is with the power. describe the boards and the sensor and how all the keys work and everything's interconnected, I wanted to address the power issue because it became almost immediately obvious once I had the thing opened up. I can tell from looking inside the power jack and kind of wiggling it a bit, it's all corroded and it's basically falling apart. I'm sure it had a lot of mechanical stress over the years because, you know, you're walking around with a wind controller and the power adapter's dangling and pulling off the bottom of the horn. So it's just falling apart. Luckily, this is a pretty standard power jack, and I have one that's almost identical in my parts store. So it looks mechanically and electrically equivalent. So hopefully it'll fit and there won't be any issues. I'll find out a little later. Regarding the batteries, that's even simpler. The positive terminal, the wire that goes from the positive terminal of the battery compartment to the power circuit on the board is simply disconnected. It looks like it was maybe a loose solder joint, and over the years it just finally gave up and fell off. So this wire is just flapping about. So hopefully just resoldering that back in place will fix the battery issue. So now let me describe the rest of the components. Let's start with the wind or the breath sensor. So at the top of the instrument there is a tube, and when you blow into it, your breath fills a chamber right here, and I'll open that up in just a sec, and then continues through the chamber, down this tube, and out a hole through the bottom of the instrument, because the moisture has to go somewhere. So let me open up this sensor unit here. It's a very simple design, but it's super effective. So let me lift the top off the chamber here. There's usually a gasket sealing this side of the chamber. It's actually at the bottom here. You can barely see it. There's a plastic gasket. And there's another flexible gasket on the bottom of the chamber, and glued to that gasket there's a coil of wire. Essentially it's an inductor. And when you blow into the instrument, this chamber fills with air. The gasket on the opposite side, the side that's on the bottom right now, pushes down, and that inductor moves up and down depending on how hard you are blowing into the chamber. Also, there's a ferrite rod fixed to the housing here, and it slips over the inductor. And as you probably know, if you move a ferrite rod in and out of an inductor, it will change the inductance. So as you blow into the chamber, the inductor moves, it moves on and off a ferrite rod, and it changes the inductance. So this is essentially a variable inductor. The leads from that inductor snake up through the circuit board that holds the buttons, and then goes down off onto the main board where there's an inductance to voltage converter. And later on I'll connect a scope up to that test point where the voltage is, and we'll see how well this breath sensor can track the pressure of your breath. Now we'll move on to the power supply board. The main body of the horn is comprised of two circuit boards, and the one on the bottom has three main functions. The first function is it's the power supply circuit. So it takes the DC power in and then generates all the required voltages for the rest of the electronics in the horn. The second function of this board is it has the power amplifier for the speaker on it. So there's a single inline package chip here and also a dip package here. These are custom Casio chips, and the pair comprises an amplifier package. I'm sure it was used in other Casio products of this vintage. And you can see the audio output on this line here goes up to the body of the horn where the speaker is. The third thing this board provides is the jacks for the audio output and also the MIDI output. Obviously, the audio output is just taking the same audio signal that goes to the speaker, and the MIDI output is taking the output from the microcontroller, which is on this other board, that comes down through these lines here through this ribbon cable. So on the upper circuit board, there's a microcontroller on one side and a series of VCF circuits for the sound generation and a VCA circuit on the bottom, and I'll get to that in just a second. So on the side with the microcontroller, there's another ribbon cable that goes up and off to some other circuit boards, and things are getting a little complicated here, but those circuit boards are where the keys and the other buttons are connected. So the microcontroller scans which keys you're pushing or which buttons you're pressing, and it generates a series of pulse waves that are fed to the analog circuits on the other side that generate the sound that the horn is supposed to produce. Also, the microcontroller generates the MIDI signals, the serial signals that go down into the MIDI jack, and also the output of the breadth circuit. So the inductance to voltage circuit output goes through an analog to digital converter, and the microcontroller reads that as well. And that's how the microcontroller can determine what aftertouch messages to send out the MIDI jack. Now on the other side of the board here, there's just some standard low-pass filter circuits and a VCA. The VCA is also controlled by the output of the breath controller circuit. So the harder you blow into the horn, the louder the sound. So that's what you would expect. One thing I should mention here is the Casio DH-100 is known to develop a squeal in its VCF circuit. So there's a feedback loop that happens in the filter circuit. And I can tell that this horn had that issue and it was repaired because I can see a yellow tantalum capacitor here. And normally, this is the capacitor that fails. And normally this should be a silver colored surface mount capacitor. So somebody in the past has fixed that issue. I'm going to fix it yet again and replace this tantalum capacitor for a few reasons. One of them is the repair is a bit dodgy, so I don't like the quality of the repair. And the other thing is I'm not sure how old this tantalum capacitor is when the repair was done, and tantalum capacitors tend to fail in a rather spectacular fashion. So I'm going to replace it with a brand new electrolytic capacitor. So at this point, I have a few things to do. I have to replace the DC power jack, and I have to resolder the positive lead to where the battery clip is, where the AA batteries go, and I have to replace that capacitor. And after I do all that, I'll hook up the output to the wind or breath tracking circuit to the scope, and we can see how well that tracks the pressure being blown into the instrument.
I'll narrate here in the background while you watch me work. The first thing was to desolder the old power jack, and then to compare the old and the new one side by side, just to make sure they were equivalent, and then solder in the new one. Then there was more desoldering to remove the old tantalum capacitor. And since the pads on the board were made for a surface mount capacitor, I had to tin them and then tack in the new electrolytic capacitor before soldering it in properly. Now I'm stripping back the lead for the battery terminal and soldering it in place.
I have things partially reassembled, and I've taken the test point for the wind sensor output, so that's the wind sensor control voltage. I've connected it to my oscilloscope and also to my voltmeter. And if I'm careful here, let me play a few notes and you can see the response on the scope. So obviously things work, and it's surprisingly sensitive. Let me do that again, and I'll do a nice slow crescendo from silence, and then I'll try some single and double tonguing. So the response is fantastic. Let me do that again, and this time we'll pay attention to the actual voltage output. So the service manual, I have it written down here. The service manual says that under full intensity, so blowing as hard as you can into the horn, you should get 2.35 to 2.4 volts output. So let's see what we get here. So we were getting about 2.5, maybe 2.6. So that seems a bit high. And also the service manual says that at rest, so when you're not blowing into the horn at all, the voltage should be 0.55 to 0.6 volts. And again, we're getting 0.65, almost 0.7 volts at rest. So it's very tempting to adjust the potentiometers to get within the specifications that it states in the service manual. But the response is so good, and I can go from silence right into a crescendo really well. I don't think I'm going to make any changes at all. Yeah, it's fine. Compared to my Yamaha WX5 wind controller, and also I play the flute, so this responds really well as a wind instrument. So I'm not making any changes. Before I get into my MIDI setup, I realized that I haven't done a demo on the built-in sounds except for the default sound. So in order, I'll cycle through the saxophone sound, then trumpet, synth reed, oboe, clarinet, flute, and finally I'll end on the saxophone sound again. This is running off batteries right now, just to show the batteries work. This is an audio out cable. I'm recording this direct with no effects. So here we go, starting with the saxophone sound. I should also mention that there is no way to turn off the vibrato. The delayed vibrato effect is permanent on all the sounds. Finally, to the MIDI setup. So I'm taking the MIDI out on the horn, it's just a standard 5-pin MIDI jack, into the MIDI to CV converter that I designed and built. And I'm doing some remapping inside the module. The first thing I'm doing is taking the pitch messages and changing them to hertz per volt, because the MS-20 Mini I'm driving runs on hertz per volt. The gate I'm changing to an S trig, or a shorting trig, again because the MS-20 Mini uses a shorting trig. And for the auxiliary CV, I'm mapping the monophonic channel pressure. I keep saying aftertouch, but it's not. It's the monophonic channel pressure, and I'm mapping that CV to the bias on the output VCA, the last VCA in the chain, and also the control voltage. for the low-pass filter to open and close it. And then the audio out, I'm passing through my Alesis MIDI Verb 2, and I'm adding way too much reverb, but I just like the sound of it. And this is what it sounds like. So you can hear as I change the intensity of the breath, the volume increases, and also I can open and close the filter. That's it for this video. Thanks for watching.